Hi everyone, so today we're going to be looking at 4.3, which looks at measures of relative position. And what this section looks at is how our data is spread out compared to our mean. So very similar to when we were looking at standard deviation and variance, but this time we're going to be using some new measurements to see how far our data is away from the mean and how spread out it is. I'm going to start out with an actual definition for an outlier. So we've talked about an outlier before, and it's just a data point that we said was really, really far away from the rest of our data points. It was uncharacteristic of the rest of our data, whereas most of our data was scattered around that mean and it was all clustered right around the same kind of point. You can have some points that are way, way off of the rest of them, and they can be really far away from the rest of the data points. And we said that that was an outlier. There is an actual mathematical definition for an outlier. It's not just a point that's really, really far away from the rest of the data points. So I want to look at that definition, and then we're going to be applying that to some examples and going into the box plots that we looked at previously in 4.1. So first of all, an outlier, I'm going to write down this definition, we're going to talk about it and then go through an example because it's not the most intuitive thing and there's a lot of definitions that arise just out of this one definition. So an outlier is a data point that is more than 1.5 times the interquartile range above Q1, above Q3 or below Q1. Okay, let's talk about this because there's a lot going on in this definition. So let's talk about what Q1, Q3 and the interquartile range are. So we discussed those right at the end of 4.1. If you remember, when we had our data sets, we talked about the mean and the median, but then I talked about the quartiles, which came out of percentiles. So the percentiles, you had a pth percentile if p% of the data was below that data point or equal to that data point, and the rest of the data was above that data point. Q1 was just the 25th percentile, okay? So the data point that was Q1, okay, whatever data point that was, meant that less than or equal to that data point, if you put all of your data in order, less than or equal to that data point was 25% of all of our data. So 25% of our data was less than or equal to that data point that we're going to label Q1. The other 75% of our data was greater than that point. Okay. Similarly, Q3 was our 75th percentile. So whatever data point we calculated that to be, 75% of our data was less than or equal to that data point that we labelled Q3. The other 25% of our data was above that data point. Now we've looked at ways of actually working this out by hand, but then we looked at a calculator, and if you actually run one variable stats on that list of data, that whatever list you have, run one variable stats on that list of data where you find your mean and your median, you're also going to find Q1 and Q3, your 25th and 75th percentile. We tend to call this Q1 the lower quartile, because if you think about it, you're separating your data into quarters here, okay? So below Q1, you have 25% of your data. Below the median, you've got 50% of your data. Below Q3, you've got 75% of your data. Okay, so you're kind of splitting this into 4 sections. And this would be the upper quartile, Q3, okay? So you've got Q1 and Q3 are your lower and upper quartiles. The interquartile range was just whatever data point Q3 was minus the data point Q1. Okay, it tells you how wide that middle 50% of your data is. It tells you how spread out that middle 50% of your data is. Okay, between Q1 and Q3, okay, you've got 50% of your data between those two data points. So the interquartile range tells you how spread out that middle 50% actually is, because you're looking at the difference between the upper data point Q3 and the lower data point Q1. So it's looking at how spread out that middle 50% is. So what you're going to do is, whenever you get a list of data, you're going to run one variable stats on it, and you're going to find Q1 and Q3. You can then find the interquartile range by just doing Q3 minus Q1. And then whatever value you get out of that, you're going to multiply this by 1.5. And then all you have to do is, whatever you get, 1.5 times the interquartile range, you're going to add it onto Q3, and you're going to subtract it from Q1. Okay? So you're just going to do Q3 plus 1.5 times the interquartile range, and you're going to do Q1 minus 1.5 times the interquartile range. Okay? Now, by doing that, this is going to give you a lower bound, Q1 minus 1.5 times the interquartile range. That will give you a low number. Q3 plus 1.5 times the interquartile range is going to give you a really high number. What you're going to do is see if any of the data points in your list lie below this value or above this value. If they do, then they are deemed to be outliers. Okay, so if they lie more than 1.5 times the interquartile range above Q3, so above the upper quartile, then they are an outlier. Or if they're below 1.5 times the interquartile range below Q1, then they are also deemed to be an outlier. I'm going to look at a quick example here. Okay, so we've got some test scores. And if you were to put this as a list in your calculator, there's a lot of numbers here, you can do it if you want. But if you were to put this as a list in your calculator, you would find that the lower quartile is 41 and the upper quartile was 66. Okay, if you type that list into your calculator and ran one variable stats on it. Now, if you find the interquartile range, okay, that's the upper quartile minus the lower quartile, which turns out to be 25. Okay, the difference between those two values. Then if I take 1.5 times the interquartile range, I get 37.5. So what I'm now going to do is I'm going to take my lower quartile and subtract 37.5, and I'm going to take my upper quartile and add 37.5. Okay, so therefore I'm looking at a low value of 3.5 and a high value of 103.5. What you really want is most of your data points, if not all of your data points, to lie between those two values. Okay, anything that lies either below 3.5 or above 103.5 is deemed to be an outlier. It is just too far away from most of the data to really be characteristic of the rest of the data. It is an outlier. Okay, so anything below 3.5 or anything above 103.5 is an outlier. That means that we have two outliers in this data. We have 2 and we have 110. So if these are test scores, okay, most of your data is kind of pretty much together. I mean, you've got some variation in here, but most of your data is kind of characteristic of each other. Then you have these two complete outliers. You have 2 and 110 that are just too far away from the rest of the data to be characteristic of it, so they are outliers. Now I want to look at something called a modified box plot. If you remember back in 4.1 right at the end, I told you about what a normal box plot was, and you guys did that in Excel for your application 2. You created box plots, okay? If you remember, with a normal box plot that we've looked at before, they are shaped kind of like this. Okay. And if you remember, this value here is the minimum data value in your list. This would be the maximum data value in your list. The middle value is the median. And then you have Q1 and Q3 are these two lines here. Okay, so you have the box in the middle, which is your middle 50% of the data. And then you have the two lines on the outside, which go out to the minimum value and the maximum value of your data. So that's what a normal box plot. So just a normal characteristic box plot. Then we're going to talk about something called a modified box plot. And what that does is it shows you the outliers in the data. Okay. Now, normally with a normal box plot, it will go those lines at the edges, which they actually call whiskers, which is why when you looked in Excel, they were called box and whisker plots. Those lines at the edges are called whiskers. They go all the way out to the minimum and maximum values. Well, if you have outliers in your data, those two lines can spread forever, all the way out to those outliers. But normally, we like to kind of discard any outliers and just focus on the data that is characteristic of one another, the data that is all kind of clustered together that actually means something to us, and almost ignore the outliers. We like to know that they're there, but we don't really want to work with them too much. Okay, so a modified box plot, what that does is instead of taking those whiskers, those lines, all the way out to the minimum and maximum values, it actually plots out the outliers and just makes those lines, the minimum and maximum value lines, they just go out to the next largest and smallest data points that are within 1.5 times the interquartile range below Q1 and above Q3. So what we've done here, okay, if we go back to our test scores, okay, we said that 2 and 110 were our outliers. So what they've done here, this is the modified box plot of that data. They at 2 and at 110 have just put a dot. It can sometimes be done as a star or a cross. And they just mark out those outliers, which you see that they've done here and here. They have then gone back to their data and looked at the rest of their data, and they've said, okay, well, after 2, our next smallest data point is 18. 18 is our smallest data point if we were to get rid of that outlier of 2. So if 18 is our next smallest data point, does that fall within 1.5 times the interquartile range away from Q1? Well, 1.5 times the interquartile range away from Q1, which is what we worked out here, was down to 3.5. So anything above 3.5 is within 1.5 times the interquartile range away from Q1. Okay, so 18 is within our limits. Okay, we are only interested in values within this range here. So above 3.5 and below 103.5. Anything outside of that is an outlier. So 18 is not an outlier. So what we're going to do is we're actually going to start our whisker at 18, at our next smallest data point that is not an outlier. If you have multiple outliers on the low end, you will plot each one of them with a star, a cross, or a circle, and then the first data point that lies within 1.5 times the interquartile range of Q1, that's where you start the whisker. Okay, then again we've got our Q1, our median, and Q3, which they've plotted out as normal with these lines and drawn it as a box. And then you want to see where the whisker goes out to for the maximum value. Now 110 was an outlier. So we need the next largest data point that is in 1.5 times the interquartile range of Q3. Okay, so we don't want to go above 1.5 times the interquartile range of Q3. If there are any more data points like that, then they are outliers. So if we go ahead and we look at our data, you'll actually see that 82, which is found here, 82 is our next largest data point. It's within this range. It's within kind of our good range. It is not considered an outlier because it is not more than 1.5 times the interquartile range away from Q3. So therefore, 82 is a good value and we are happy with it. and that is where our whisker goes out to for our maximum value. So a modified box plot just stars out where the outliers are, and then the whiskers just go out to the next smallest and next largest data point that are within the kind of good range that we like to look at. I'm actually going to do an example later on to show you how to do this on a calculator, because you are actually able to draw box plots and modified box plots on a calculator. So then you can see if there are outliers in your data without going through a ton of calculations. Okay, next I want to look at z-scores. This is going to help us out as we go into looking at different types of distribution in chapters, I think it's chapters 7 and 8 is when we start looking at distributions. And we're going to look at the normal distribution, binomial distribution, etc. But z-scores are really useful when we look at normal distribution. There is actually an against all odds video. If you again go down to the tab of against all odds videos in Blackboard, and there is one called normal calculations. Again, it's one of these videos that has a lot of info in it that you may not yet understand, that we have not covered in this course yet. It is a good video and kind of shows you how z-scores are used in normal distribution. So it kind of shows you where we're going to be going in this course, even though you may not all understand the whole video. But I have put that in there. So if you go to against all odds videos on Blackboard, and there is one called normal calculations, you can go ahead and watch that, and it shows you how z-scores relate to some other stuff in statistics that we're going to cover later on. But what a z-score does is it's another standardized measure of the relative position of a data point with respect to the mean. So rather than looking at all of the data this time and seeing how spread out all of our data is compared to the mean and given a measurement for that, it's actually looking at a single data point and telling us some kind of measurement of how far it is away from the mean. Okay, so what it does is it transforms the data value into the number of standard deviations that the value is away from the mean. So rather than just saying, oh, it's, let's say you had a mean of 5 and your data point was 8 that you were looking at, rather than saying, well, I'm 3 above the mean, it's going to look at what the standard deviation is. Let's say our standard deviation was 1.5. So if we had, this is just a very quick example, if we had a mean of 5 and the data point that we were looking at in this sample was 8, okay? And let's say that our standard deviation for this sample was 1.5, okay? Now, you know that our data point of 8 is 3 above the mean, okay? But what I could also say is, well, my data point of 8 is 2 standard deviations above the mean, okay? 2 times 1.5 is 3. So I can also say, well, I'm 2 standard deviations above the mean. Rather than just saying I'm 3 away from the mean, I'm 2 standard deviations above. So a z-score is a way of measuring how far a data point is away from the mean by using the standard deviation. Okay? So a z-score for any particular data point, we'll call it x. So any x data point in your list of data, okay? Its z-score, which is the number of standard deviations away from the mean, okay, it depends if you're looking at, of course, a population or a sample. So for a population, it would be that. For a sample, we would be looking at that. So this is for a population, and this is for a sample. Okay, so all a z-score tells you how many standard deviations data point is away from the mean. Okay, so it's calculating this measurement in terms of standard deviations rather than just in a numerical value of how far above or below that data point is. Okay. Why do we like this? Well, as I said before, if you just say, let's say I'm looking at that this data above here was in feet. Okay. Remember that the standard deviation always has the same unit as your data. Okay, that's why we like the standard deviation. Well, if I go ahead and calculate a z-score, so it's the data point minus the mean divided by the standard deviation, okay, you actually get a unit-free measurement. A z-score has no units because your data point x, in this case would be in feet, minus the mean, which is also in feet, so you're still in feet, but then I'm dividing by something that is in that same unit. So I've got something in feet divided by something in feet. I just get an actual integer out, okay? It has no units. So we like z-scores because they are unit free, okay? So z-scores are unit free. Okay. Again, I'll just write out the population version of this here. Okay. The z-score for this data point x, let's think about when it's going to be positive and when it's going to be negative. Okay. Your standard deviation for a sample, for a population, whichever one you have, your standard deviation is always positive. Okay, regardless of what data you have, it's always positive. Okay. So now we need to look at the difference between our data point and the mean. Okay. If your data point is above the mean, that means that x minus the mean is going to be positive. So if your data point is above the mean, then the difference between the data point and the mean is positive. Then you're dividing by something that's positive. So if your data point is above the mean, the z-score will be positive. So if your data point x is greater than the mean, the z-score for that data point is positive. Okay. Now, if it's below the mean, so if x is less than the mean, then if I do x minus the mean, I'm going to get a negative number. But the standard deviation is still positive. So then I've got a negative number divided by a positive number, which is negative. So if a data point x is less than the mean, the z-score for that data point is negative. Okay, so the reason we like z-scores is because they're unit free. Every single data point in your list of data is going to have an associated z-score, and the z-score just tells you how many standard deviations that data point is away from the mean. So it tells you how far a data point is from the mean, but talking in terms of numbers of standard deviations away from the mean, rather than just telling you the distance away from the mean. Okay, so it just gives you a unit-free way of showing us how far a data point is away from the mean. Okay, here's an example of where we're going to be using z-scores. So it says, suppose you scored an 86 on your biology test and a 94 on your psychology test. So if we look at this, you think, okay, on my psychology test I got an A, and on my biology test I got a B. So I obviously did better in my psychology test. Then what they've done is they've looked at the mean and the standard deviations for the whole class for these two tests. So in my biology class, the mean for that test was 74 and the standard deviation was 10. And for my psychology class, the mean was 82 and the standard deviation was 11. What I'm going to do is I'm going to find the z-scores for each one of these tests to tell me how far away my test scores were away from the mean for the whole class, to tell me how well I did in comparison to the rest of the class. Okay, so let's go ahead and do that. So my z-score for my biology test, let's start with that one. So z is equal to, well, my data point, my test score was 86, minus the mean of 74, divided by the standard deviation, which was 10. Which, if you work that out, would be 12 divided by 10, which is 1.2. Then the z-score for psychology was, my data point was 94, minus the mean for the class was 82, divided by 11, which I again was 12 above the mean, but the standard deviation was 11, which means that if you calculate that, it comes out to roughly 1.09. Okay, so let's look at these two z-scores. What this tells me is that in my biology test, I was 1.2 times the standard deviation above the mean. Okay, if this was negative, if my z-scores were negative, it would mean that I would have done worse than what the mean was. So I've done worse than average. Okay, but because these are both positive values, they're better than the mean, they're greater than the mean. Okay, so my z-score for biology was 1.2. So I was 1.2 times the standard deviation above the mean. And for psychology, I was 1.09 times the standard deviation above the mean. So in relative positions compared to the mean, I actually did better in my biology class than in my psychology class. I was actually more standard deviations above the mean in my biology class. So I actually, in comparison to the rest of my class, did better in biology than I did in psychology. Okay, so that is where z-scores are useful. They are really useful when you are looking at comparisons for two different data sets. Okay, because they can tell you for different data points how far above or below the mean you were, and then you can compare them for different data points and for different data sets. Okay, so now I want to look at how to actually plot these box plots that we were talking about before, both the box plot and the modified box plot, on a calculator. This is really, really useful when you are given multiple lists of data and you want to compare their spread and you want to compare the values and the outliers in the data. So this is a really, really useful tool that we actually have on these TI calculators. So what I have here, if I go to Stat and Edit, I have two lists in my calculator. Okay, list 1 is just a list of average lifespans of different mammals. So we've got different species and it is their average lifespan. Then in list 2, for those same mammals, it is their longest lifespan in captivity. Okay, so we have the average lifespan of a mammal, and then we have the longest lifespan of that same mammal for each one of our mammals when they are living in captivity. So I actually have 40 data points for each one of my lists. So I've got 40 different mammals. So what I'm going to do is I'm going to plot these box plots. So what you're actually going to do, if you ever need to do this, you go to Second, and this button up here that says Stat Plot. So Second and Stat Plot. And then you'll see that we have 3 different options, okay, plot 1, plot 2, plot 3. Let's start with plot 1, so click enter on that.
you can actually plot multiple different types of graphs. You could do bar graphs on here, you can do scatter plots, which we will actually do in chapter 5. You can do line graphs, but you can also do these box plots. Now there are two different options here for box plots. Both of these are different types of box plots. The one on the right here, this is a normal box plot. Okay, so it's going to put a line at the minimum value and a line at the maximum value, and it's going to put the boxes and the whiskers exactly like you would normally expect. This one on the left is actually the modified box plots. They're going to do exactly as we talked about before. They're going to star out where those outliers are, and then put the lines and the whiskers are going to start at the next smallest and next largest data points that are not outliers. So they're within 1.5 times the interquartile range of both Q1 and Q3. Okay, so they're inside that range. Let's start out with a normal box plot. So I'm going to click enter on that one. Then I want to do, this box plot is going to be for list 1. Then I'm going to do a second box plot for list 2, but it will actually put both of them on the same graph. So this one is for list 1, so this will be the box plot for the average lifespan of those mammals. Frequency keep as 1, and make sure that you have the plot on. Okay, so make sure if you're up here, make sure you haven't got it clicked as off, make sure it is on. Then coming back up to the top, let's go to plot 2. Okay, again, make sure you've got it turned on. Then the type of graph that I want to do, again, I'm just going to do a normal box plot. This is going to be for list 2. You may have to change this if it's got something else in there. Just do second and 2 to get list 2. And then I'm going to make sure that plot 3, let me come up here, I'm going to make sure that plot 3 is turned off. Okay, I only want to plot 1 and plot 2 for list 1 and list 2. So once you have done that and you have clicked the appropriate graphs, you're going to go to this zoom button at the top. So click that. And you want to go down to zoom stat, which is number 9. So go to zoom and then go to number 9. And if you do that, it will plot those box plots for you. Okay. You can actually, using the arrows, trace along these values just like this. If you wanted to see where the minimum and maximum values were, you can just trace along those lines. You can see where your interquartile, how long your interquartile range is, because you can see what Q3 and Q1 are. And you can also see what the median is if you trace along. Okay, so this is how we get our box plots. Okay. Now we can see that we have a much wider spread of data for the longest lifespan of these mammals in captivity. Okay, that data is more spread out. That means that in captivity we have some mammals that don't live very long, but we do have some mammals that in captivity live an incredibly long time. And what we see from this data here for the average lifespan of our mammals, we actually see that on average, most of these mammals, okay, the middle 50% of our data is really, really close together, okay, it's clustered really close together. So most of these mammals actually live around the same amount of time, okay, because you have a lot of that data, that middle 50% of the data is clustered really close together, unlike what we have with this box plot. Okay, so that data would be more spread out for the second box plot. So that's what this shows you. Okay, that's why this is useful. Let's go back. I'm going to quit out of that and I'm going to go back into stat plot again. And this time I'm going to do a modified box plot. So this time I want it to show me the outliers and leave that box and the whiskers just for the data that is kind of characteristic of the rest of the data. So the data that is mostly clustered together and not those outliers. Those outliers are going to be starred out. So you can change what mark you want to mark the outliers with. I've just put a cross. And then we're going to do the same thing for plot 2 to see if we've got any outliers in that data. Okay. So now, if I go to zoom and number 9 and I plot these, we actually see that there are no outliers for the captivity data, but there are outliers for our average lifespan of mammals, okay? We have some of these mammals whose average lifespan is actually way longer than most of our mammals. So we have all of this data is clustered really close together, unlike this data here where it's really spread apart, okay? So that's why this is useful. So if you ever need to do a box plot, you can do that. You can also do a modified box plot where we're going to star out those outliers, but it's great to see how spread out the data is and compare that to other data sets.